Okay, so let's get started. Can people on Zoom hear me? Can I get the signal? Okay, perfect. Okay, so we have been talking about database system for 2 weeks now, right? So today is actually the lecture actually put everything together, okay? We'll talk about computer systems. It's always layer by layer by layer. And sometimes we start from the bottom layer, and it could a little bit, boring, right? So all those details. And today will be actually we talk about the top layer, and that's actually the lecture going to actually talk about everything that we have been doing, and also like how they actually fit together. So let's just use the first 10 minutes, okay, to just refresh your memory about what we have been talking about, and also let's go through the layer by layer in the database system to really make sure we are on the same page what we are talking about, and then we can actually put them together. So we have been doing this. You have the database system in the middle, and you as a user, and then try to interact with your data infrastructure, your DRAM, your hard drive, right? And you interact with this database system by issuing SQL queries, and whenever you ask the database system to actually bring information to you, what the system is going to do is actually try to understand how to bring information all the way from the hard drive to the DRAM and to you as a user. So we have been talking about the thing on the left-hand side. That is how that database actually do that. And we talk about this, right? So this layer-by-layer structure of a database system. In the bottom layer, right, there's a disk manager, there's a buffer manager, there's an access method, there's operator execution layer. And we have been talking about all these 4 different layers. And today, we are going to talk about the top layer, which is query optimization. But before we talk about query optimization, let's just really quickly go through every single layer to make sure we understand what they are actually doing. Essentially, whenever you have information inside your database, it will be stored inside your hard drive as a collection of files, right? So 2 weeks ago, we actually went through the process of trying to open up that file in SQLite and try to edit it, if you remember. That's where your information actually sit. The bottom layer of a database system, at least in the traditional way, is actually the disk manager. The goal of that layer is try to make sure there's something that interacting with the hard drive, allocating pages, deleting pages, fetch pages, right? The goal is really make sure every single layer above that will not interact with the hard drive. And then you have the layer above it, the buffer manager. Why doing the buffer manager? Because inside your computer system today, there is that storage hierarchy. There's a hard drive, there's a main memory, they have different speed, they have different size. You do not want all the other layers deal with that hierarchy. The goal of the buffer pool manager is really try to understand we can provide this illusion that all the data are already inside memory, not on disk, for all the layer above it. The functionality that they try to provide, including actually fetch a page, return a page, update a page, so on and so forth. It's relatively simple, right? So all the upper layer will talk to the buffer manager to say, yeah, give me the yellow page. And then the buffer manager will check whether the page is inside DRAM or not. If it's already in DRAM, return it. Otherwise, using whatever strategy that we have been talking about to try to pick a page to evict, and then fetch the right page, and then return that to the upper layer. Once you have this, all the upper layer will actually just talk to the buffer manager to get the page instead of fetching page and managing this buffer by themselves. And then the layer above it is the access method. In this way, we do not want the upper layer to fetch pages. We want them to interact with the buffer pool manager via the access method layer by just calling those high-level abstraction about how to access data. This layer is really where we provide different ways of accessing information inside a relation. You can do screenshot scan, right? Just scan this relation. You can do B+tree index. You can do index lookup. You can do hash table, so on and so forth. So the interface you have to the upper layer is really all those higher level abstraction to access information in a table without interacting with the buffer, without interacting with the disk manager. So this is actually something that we have been talking about last time, right? For example, you could build a hash table, right, over your relation, right? One thing you could do is you can just hash all those values, right, into different slots inside your hash table, and then for each slot, you can actually put there the record ID, which is a pair of page ID and slot ID, pointing to the original tuple. Once you have this, right, you can start to do lookup using this hash table as one of your access methods. And then there's the layer above it, which is the operator execution. Because all those access methods is still a little bit too low level for us, right? They are screenshot scan, all the type of things. But we want to implement even higher level of abstraction by using those access methods. And that is what we have been talking about on Wednesday, which is how can we support a whole bunch of relational algebra operators like selection, projection, join, all the type of things, right? How can we support those by implementing those using all those access methods that we have? And we talk about for each one of these operators, we have so many different ways to implement them because we have different access methods that we can provide on the same relation. So this is just a join operator, and we talk about these 5 different ways that you can do join last time. And for each of those, there are the cases that it could be applied. Not all of those methods apply to all the possible joins, right? So, and then for each of those methods, we also talk about the cost model. This is our expected cost of running those operators. So today, we are going to talk about the top layer, which is query optimization. And this is a layer that we actually take as input a SQL query, and then run it and give back the result. Essentially, what's going to happen is given a SQL query, we try to generate a good execution plan. As you will see, an execution plan is a tree of relational algebra operators. And for each of those relational algebra operators, you also have a markup to say, yeah, this is how I want to run it. Because there are so many different ways you can run the same operator. And then you are going to use the operator execution layer to actually run it. So these are the 2 things that we are going to talk about today. Let's talk about query optimization first. So at this step, what do we have? The input to this step is this very familiar SQL query that we have, right? I just want to join these 2 relations on the ID attribute. But the database cannot just run this for you because it doesn't really know how to do that. Database being a declarative system means that as a user, you never tell the database system how to actually run this query for you. You just tell database, yeah, this is what I want. So given this, what happens inside most of the system is that it's going to generate what we call a logical plan that essentially tell the database logically what the user really wants in a very precise way. So this is one example logical plan. It emits a tree, right? So, and then for every single node, it is a relational algebra operator. And then the leaf node is relations, right? So given this, it's a precise description of what the user wants. But still, the database cannot take this and actually run it because there are missing informations. Because for every single operator, I have no idea how to actually run it. We talk about 5 different ways that you can run this join operator. And we talk about 3 different ways you can run the selection operator. And also, it's not really clear whether this plan is actually optimal. So for example, in this case, you have a 3-way join between these 3 different relations. Whether I should join the first 2 relations together or whether I should join the second or third relation together is not really clear. The goal of the query optimization layer that we are going to talk about today is to take as input this logical plan and generate a physical plan. What do we mean by a physical plan? A physical plan will be, first one, equivalent to the logical plan. They need to return the same thing. And second, the database is going to play with the structure of this plan. Join order, other type of things, right? Try to rewrite this plan. And then for every single operator you have inside this physical plan, is going to tell you how I'm going to actually run it. For this join, I'm going to do sort merge join. For that join, I'm going to do next loop join, so on and so forth. The goal of the physical plan is the database can take that and actually call the operator execution layer that we talked about on Wednesday, and then give you the result. So that is a functionality we want to enable today. And then if you look at this, there are two fundamental questions in building a query optimization layer. The first one is actually how to run a physical plan. Okay? So given a physical plan, how to run it. Yeah, we talk about a physical plan as a DAG or tree of physical operators. Yeah, but there are so many different ways that you can see to actually run it. Okay? How to run it, given that we know how to run each operator. And second question is actually how to search for the best physical plan to actually use. We are going to talk about these two questions. They are not independent because given how you are going to run this plan, you have different ways for you to search for the best plan. So now let's talk about essentially the first question. So so we look at this, two questions. They can also be decoupled into essentially four different things that we need to understand. The first one is the execution model. That is, we know how to run a single operator now. How can we put them together? Now I have a tree of those. How can I pass information between those operators? There's so many different ways you can do that. Once I know that, there's a cost model. That is, given this physical plan, how can we estimate the cost of running that plan? Okay? We talked about how to run that for a single operator last time, but now we need to put them together to understand how to run the whole thing. And then we try to define the search space. Right? You give me a logical plan. There are so many different ways I can run it. What is the search space looks like? Okay? And then the fourth question is, given the search space, given the cost model, how can I search it? Because that search space could be pretty big. How can I effectively or efficiently, or both, try to search within that it's a search space, try to find the optimal plan. So these are the four things that we are going to talk about today. Now let's start from the execution model, because that's important. And without knowing how those operators are being put together, it's very hard for us to reason about how to estimate its cost. So there are different ways that these operators can be put together. So there's Iterator model we are going to talk about today. There's something called materialization model, and there's a whole bunch of things in between. The most popular one will be the Iterator model. Essentially, the high-level idea is to think about each of those physical operators as an iterator. Okay? It returns a stream of tuples. So that is how to think about every single node in the tree. It takes as input a stream of tuples coming from the operator in the child node, and then it output also a stream of tuples. Because we are talking about streams, right? So essentially, the thing that we are actually providing is for each of those operators, there's a function called next. Give me the next tuple in the stream. And then what's going to happen when running all those physical, like this physical plan, is someone is going to call essentially the next tuple from the root. Okay? So take this query plan, for example. Okay? It's a three-way join. I join R and S using next loop join. Then I join the result of that using next loop join with T. That is my physical plan. And then to run that in the iterator model, someone is going to call the next function of the root node. Give me the next tuple, right? So like from this execution plan. And then what's going to happen, right, as you can imagine, is we are going to actually call the next tuple of the leaf node. For example, then we start to call the next tuple of the next loop join operator, which will actually call the next tuple of the left child node, which is a next loop join operator. And then that next loop join operator is going to call, for example, the next function of the scan operator on the left. Because really try to do next loop join, right? They try to scan the left relation For each one of them, it tries to scan the right relation. That's next loop join. So essentially, once you have this call next from the root, it's going to propagate that. And then once you have this next call on the R relation, which is a scan, you get one tuple from R. And then to get the next tuple from the next loop join operator, it needs to sequentially scan this relation S. So it's keep calling the next operator from relation S. Every single time you call it, it's going to give you one relation back. For example, S1 in this case. And then you are going to match with R1. And whenever you have a match, you are going to return that. Right? For example, R1, S1, R1, S2 is a match. Then you are going to return that to the parent. Okay? And you keep doing this. And then you have your result. This is sometimes called a Volcano model. Well, since that is like a run like a volcano, right? So all the way from the bottom to the top. Okay? And then how to get the next tuple, right? You just call the next function from the root. So far so clear, right? So I mean, it's a very natural way of running this DAG of operators. Okay? But this is not the only way. An alternative way of doing that is what people call, let's look at what's good about this. So essentially, the good thing about this is provide a pretty generic abstraction for pretty much all the operators, right? You are hiding a whole bunch of information about what that operator is actually trying to do. In this model, all the operators actually take as input a whole bunch of streams and output another stream. It's very easy for them to put them together. It's very easy to implement like iterators, okay? And also, one thing that's interesting is sometimes you can actually pipeline those kind of operators together, right? You do not need to store the result in the middle, and you can just pipeline them, right? Because every single time, your parent only wants a single tuple from you. Okay? You do not need to keep all those results. And suppose kind of essentially, parallelism and distribution, right? So the best thing about this is every single time you want a tuple, you have a whole bunch of function calls in the system, right? You start from the next function call from the root, and then you propagate that. Every single time you go one layer down, you are actually talk about a whole bunch of function calls. That could be pretty slow. And another thing is the instruction cache locality could be pretty bad, right? In this case, because every single time I'm calling the next for one operator, it's actually do one thing. It's actually try to produce one tuple. So, and then the system actually try to switch to other things. So in this case, the instruction cache locality might not be the ideal case. So this is a little bit abstract, but it's going to become very clear when we talk about the alternative. Another extreme of putting them together is what people call motorization model. The high-level idea is that instead of treating each operator, physical operator, as a function that map a stream to a stream, I think about every single physical operator as a function that actually map a relation, a whole bunch of relations, to a relation. Essentially, under motorization model, every single operator will actually process all the input and output the whole thing, store it somewhere, and then you go up one layer, okay? In the iterator model, you're actually producing a tuple by tuple. That's how you think about those operators. Here, I'm producing all the output at once. So for example, one thing that we can do in this case is to run this, I will first run the next loop join operator on the left-hand side. I'm going to take R, take S, I just output this relation. I write it somewhere. And then I will run the operator above it. Then it will generate a whole relation, return to the application. Okay? Instead of having this volcano type of execution, like all the way from the top, and you have layer of propagation of the next function. Here, I just say, okay, just output everything, store it somewhere, go up one layer, do that again, until you reach the root. So this is the alternative way of thinking about what those operators really mean. they are not a function over streams. They are function over relations. So what's the good thing about this? The good thing about this is that it could be pretty efficient when your intermediate result is not too much larger than the input, which we shouldn't take for granted because there will be cases that your intermediate result is very, very big. For example, you have R join S, and you have a very big fan out. Okay? It's a cross product, for example. Your intermediate result could be really, really big. In that case, writing them down will be actually very expensive. So, but if your intermediate result is not that big, yeah, you can just write it down. The consequence of that is you pay extra I/O because you need to save the intermediate result, but that's fine. And then there are things in the middle. The things in the middle, sometimes called vectorization model, is very similar to the iterator model in the sense that you do have this propagation of the next call. It's also similar to the materialization model in the sense that every single time I call the next, instead of giving me a single tuple, you give me a batch of tuples. Okay? So essentially, every single time I call next, you give me multiple tuples. Okay? You do a small batch instead of a single one. It's actually it's interesting because that's kind of something in the middle. It sometimes get good property for both of this, right? So it kind of can reduce the number of function calls compared with the iterator model because every single time I call it, you give me a batch, not a single one. And then it also allows for optimization like SIMD or AVX because now I start to access or process a batch of tuples. So sometimes people do this, okay? So this is the 3 different ways of actually running things. So, and then in practice, there are actually more. So in this lecture, let's assume we are going to do this in the iterator model because that's a little bit easier for us to reason about it. So once we decide on the execution model, the second thing is about the search space. Essentially, in this case, giving an input logical plan. Okay? Giving a SQL query, you parse it, you have logical plan. There are so many different ways that you can construct a physical plan that give you the same thing. The goal of the second step is really try to understand how can we construct that search space. What are the candidate plans that we are going to search for when we actually run it? So there could be different join order, right? So there could be different cases when the selection can happen, right? So you can actually push down your selection to the bottom, right? All those type of things, so on and so forth. But high-level goal is take us a plan on the left-hand side and try to think about how can we construct an equivalent plan, the thing on the right-hand side. So there are actually multiple ways you can do it. The way that we are going to talk about today is that we are going to define a whole bunch of transformations. We call them query rewriting rule, which actually something take as input a plan and generate a new plan. And then we will make sure if you rewrite your plan in this way or transform your plan in this way, you are going to get something equivalent. So that is how we want to think about it. Essentially, the input of a transformation is a relational algebra expression E, and the output is E prime. The contract we have by applying that transformation is that E prime and E going to be equivalent. What do we mean by that? By being equivalent, it means that if you give me any of the database instance, you run E prime, the result will be the same. So this is what we mean by something being equivalent. Okay, now let's talk about a whole bunch of those rules. Some of them are actually pretty natural. So the first rule people often use is, conjunctive selection operations can be actually deconstructed into a sequence of individual selections. So this is what we mean. Assuming in the original query plan, when user writing that SQL query, you have a selection operator with 2 conditions, theta 1 and theta 2 over something. Okay? So this can be decomposed into 2 different selection operators. You do the selection of theta 2 first, and then once you get the result, you do the selection of theta 1. This is very natural, okay? But let's try to go through the process once about how to prove it, right? Then you know how to do that for the other rules. So how to prove this? How to prove this transformation from the left-hand side to the right-hand side is actually give you something equivalent. I mean, in this case, right, so what can you do? You can try to reason about what you have from the left-hand side, right? So this is going to give you all the tuples that in E, in the input, satisfy the condition that theta 1 and theta 2 as a predicate applied over T is true, right? That's the definition of the selection on the left-hand side. And then you have the definition on the right-hand side, which is it's going to give you all the tuple E that if you apply theta 1 on it, it's going to be true. And then if you apply theta 2 on it, it's also going to be true. And as you can see, it's very easy to see whatever instance you give me, whatever E you give me, the left-hand side is going to be a subset of the right-hand side, the right-hand side is going to be a subset of the left-hand side, so they are actually equivalent. Okay? So this is a very simple way to think about whether this transformation is valid. But intuitively, this makes sense, right? When I have the conjunction of predicates, I can decompose it into something smaller. Okay? Many other rules, like this one, might look a little bit trivial, but there's always a proof underneath the cover to make sure your query optimization layer will do something actually correct. Intuitively, in a graphical way, right? So it's actually transform a plan on the left-hand side. You have a single selection operator with two predicates into something look like the thing on the right-hand side. Okay? It's going to decompose that into two different selection operators. It's going to become clear why we want to do that, okay? Really, really soon. The second thing is if you have these two different selection operator, you can actually switch their order, and that's fun. Okay? I have theta 1 applied to theta 2 is equivalent as I apply theta 1 and then apply theta 2. Okay? You can just change the order. In a graphical way, right? If you give you the plan on the left-hand side with theta 1 as a parent and theta 2 as a child, you can swap the order. It's fun. Okay? It's relatively easy for you to see how to prove that. We are not going through the formal proof, but this is another thing you can do on your query plan. And you can do more. Okay? Another thing you can do is assuming you have two projections, T1 and T2, and assume that T1 is a subset of T2. Actually, T1 must be a subset of T2, otherwise you will run out of things to project on, right? So T1 is a subset of T2. That's why the thing on the left-hand side is valid. You can just get rid of T2. Okay? So here you can start to see your plan get a little bit simpler. Okay? If the user have two projection operators in the plan as input, you can just get rid of T2 because, yeah, T1 is a subset, right? Projection, if you project the whole thing onto T1, yeah, it's the same as you project onto T2 first and then onto T1. Okay? Make sense? This is really natural. Okay? And you can do more. Assuming you have a cross product between E1 and E2, these two expressions, and then you do the selection after you do the cross product, that's equivalent as just doing a join between E1 and E2 with predicate theta. Okay? And another thing is assuming you already have a join, you are joining E1 and E2 on predicate theta 2, then you do a selection after it, it's equivalent that you do one join with a predicate theta 1 and theta 2. So essentially, graphically look like this. If you have these two operators, one is a cross product, another is a join operator, and then you do a selection over the result of the join or cross product, you can actually push your selection operator into the join. Okay? This is something pretty natural, right? And then there are other things, there are other transformations you can do. So join is commutative, right? Essentially, you have E1 join E2 is the same as E2 join E1, right? So this actually becomes interesting when you have, I mean, if you only have a two-way join, it's not that interesting. But when you have this three-way join, okay, you have the first relation join with the result of second join the third. You can actually change the structure of this join tree then you can join this first two relations first, then you join with the third relation. When will this become useful? This will become useful if the result of relation 1 join relation 2 is actually much, much smaller, right? So, and then sometimes the thing on the right-hand side will be much, much faster than the thing on the left-hand side, okay? And they can do more, right? So natural join operations are associative, right, in the sense that if you have E1, natural join E2, then natural join E3, that's the same as E1, natural join the result of E2 join E3, right? That's going to look something like this. Theta join is also associative, right? Under some very mild condition. So essentially, it's going to look like this. I have more. Whenever you have E1 natural join E2, this is actually something very interesting. When you have E1 join E2, and then you do selection over the result, if your selection predicate only involve like a attribute on E1, what you can do is you can actually push down this selection. Instead of doing the join first and then do the selection, you could do the selection first and then do the join. This is one of the most important operations that most of the query optimizers are going to do that for you. Okay? Because join, as we can see, is one of the most, well, I mean, it's one of the most expensive operators inside relational database system. You want the input to be as small as possible. So often what the query optimizer try to do is try to push down your selection as much as possible. I want to filter out result as early as possible before I do the join. And this transformation is going to allow you to do that. If I have a query tree on the left-hand side, I have a join and then have a selection, it's equivalent to you have the selection, then you do the join, assuming the selection predicate only involve a single relation. Okay? So the high-level idea is if you compare the number of tuples on these two different edges that are highlighted in orange, essentially the thing on the left-hand side is going to have more tuples compared with the thing on the right-hand side, because I start to do the selection earlier on the right-hand side. And then you can actually push down more operators. Assuming I have this join between E1 and E2, and then I do projection onto two collections of attributes, L1 and L2. You can actually push them down, right? You don't have to do join first, and then you do projection. You can do projection first, the thing on the right-hand side. You can do the projection first, and then you do the join. Okay, makes sense? And there are more, okay? So the intersection and the union between two relations, right? You can actually exchange the order, something like this. And then they are also associative. You can union them in different ways. So, and then, right, when you have selection and set intersection and set difference, right, you can actually distribute them in different way, right? So this is actually pretty natural. One example is assuming you have selection over a union, you can do the union over the selection. Okay? That's another thing you can do. You can also push down selection over the union operator. So, and then there are more. Assuming you have projection over a union, right? You can also do the union over projection. Okay? So these are all those interesting operations you can do. Here, we just take a part of the subgraph of the query plan, and then you can do the transformation. Once you have this, you can actually put them together, apply them one by one, then you have a really big search space, as you can see. So this is just one example. Okay? So this is one example, I think, in the textbook. In the input, what do I have? In the input, I could have that relational algebra expression. What I do is I have three different relations. I have branch, account, depositor, right? So I can join the second and third relation, and then join with the first one, then do a selection, then do a projection. This is something you can write in select from where, right? It's going to look like that. And then you can actually transform this step by step. You could first say, yeah, transformation. So I will try to do the join associativity thing, right? Then I join the first two relations first, then join with the third one, and then I push down my selection. Okay? Then I actually push down the sum of the selection thing over the first join, right? And then I can push down selection even more. I can push down sum of the selection to branch, sum of the selection to account, so on and so forth. So this will actually transform step by step the query plan on the left-hand side into the query plan on the right-hand side. And if you compare these two, it's very easy to see the thing on the right-hand side will be much cheaper to run than the thing on the left-hand side. Why? Because selection usually is very cheap. Once I do the selection earlier, when I do the join, which is actually very expensive, often quadratic, well, I mean quadratic in computation, but I mean, okay, so it could be quadratic, okay? So it could be very expensive over something much, much smaller compared with the thing on the left-hand side. But another thing to look at is the thing on the left-hand side is actually the most natural thing that your user could be thinking about. When you are writing a select from where query, what the user actually thinking about might be the thing on the left-hand side. It doesn't matter what the user gave you. The system is going to automatically search for the optimal thing to run for the user, which is the thing on the right-hand side. So there's a whole bunch of transformations you can do over the input query plan. And now the third question that we need to understand is now I have this search space. Okay, given an input, I have a whole bunch of possible transformations I can do. I can apply a whole bunch of those and then get a whole bunch of candidate query plan. How can I pick the best one to use? Well, it's very easy to say what you should do, right? For each of those candidate plan, I estimate the cost and I pick the best one, right? It's as simple as that. But it's actually become a little bit hard to do because of multiple things. The fundamental question is, if you give me a query plan that you know is equivalent to the input, how can I actually estimate the cost without running it? That's actually not that trivial. How can I estimate the performance? So if you look at this, there are two fundamental questions that we kind of need to understand. The first one is, because my plan is a DAG or tree of operators, I want to understand how to estimate the cost of running a single operator. And then the second question is I want to understand how can we combine those multiple operators together to have the cost of the whole plan. That is the two fundamental questions that we want to understand. So the second one is kind of slightly easier than the first one. Okay? So we are going to look at the first one first. So now, how can we estimate the performance of a single operator? So that is something we have been talking about actually on Wednesday, or actually in the last 2 weeks. That is the exercise we have been keep doing and doing and doing. Right? It's for every single access method, for every single operator, we have that cost model. We try to estimate how expensive that could be. You can count a whole bunch of things, but in this course, we count the number of data movement, those I/O, from the hard drive to your memory, because in most of the traditional architecture, that is the bottleneck. So just to refresh your memory, assuming you want to do this selection operator, right? You could have so many different ways to run that. You could do a scan over the heap file to implement selection. You can do, if you have unclustered B plus tree, right, it's going to look like this. You can also probe it using like cluster B plus tree, something like this. So for each of these different ways to implement this operator, you have different cost. But one thing that kind of little bit makes this problem challenging is you see there is a fundamental factor, that alpha, which is the selectivity of this selection operator, that actually tell you how many tuples am I really expecting in my output. If I do not know about that, there's no way I can estimate the cost of this operator precisely. Because how fast, how slow, which one's faster, which one's slower, actually heavily depends on how many tuples I'm really expecting out of this operator. And also, if you think about putting the whole thing as a tree, the root operator really need to know how many tuples I'm expecting from my children, and then so on and so forth, right? So that's actually very, very important. Selectivity of a single operator is one of the most fundamental things you need to estimate inside your query optimization layer. And that could be really, really hard. So the problem we want to understand, the name is called cardinality estimation. We try to understand the cardinality of the result. Very hard. People have been working on that for half a century, and they're still not done. It's far away from being done. Okay? So from the complexity perspective, it's sharply complete. It's as hard as you can imagine. The hardness, it's extremely hard. Trust me. Yeah. So, but we only cover the basics about how to do this. If you have essentially the way to think about cardinality estimation in the modern way is I have this relation on the left-hand side. I want to summarize it into some data structure, that black box in the middle. And then such that if I have a query, I have a single operator, I can take that black box and try to estimate how many tuples that operator is going to return for me. And then we are trying to build that black box. There are so many different ways you can build a black box. A very natural way, for example, is I could just subsample 10% of my relation. Right? Whenever you have that operator, I run it on a smaller one, and then multiply the result by 10. Right? I could do that. There's nothing stopping me from doing that. And actually, in many systems, they actually do it. They have a subsample of a relation, and they just run to see what happens. But there are other ways to construct a black box that's going to be cheaper than maintaining a subsample. For example, if you want to understand the selectivity over a discrete attribute, for example, here I'm giving, for example, the age of a person. Once you can do is you can build a histogram over that attribute. Right? I can give me a relation, I can just sequentially scan it and try to count essentially, how many tuples have age equals 0, how many tuples have age equals 1, so on and so forth. Okay? That can be my black box. And then given an operator, for example, select age equals 5 over this relation, I can just look up over my histogram to say, there are 5 people here. I don't know which 5 people, I don't know which 5 tuple, but I can tell you, if you run that relational algebra operator selection over this relation, you are going to have 5 tuples in the output. It's as simple as that, okay? And you can do this for example, for 2 different attributes, right? For example, you could have this selection operator to say, I want to do selection, age equals to 2, right? Postcode equals to 8006, for example, over this relation, right? You could have the histogram for the age, for the postcode, right? Then you can actually combine them. But if you think about this, it's actually not clear how to combine it. Because I have histogram for every single attribute, but now I want the conjunction. I know how many people with age equals to 2. I know how much people with postcode 8006. But if you only build this histogram for a single attribute, I actually do not know their correlation. So what should I do? This has actually become really hard. This is actually why cardinality estimation is a fundamentally hard problem. Because you are trying to capture correlations, exponential many correlations, using a small data structure. That is fundamentally why this is a hard problem. Well, what people do, the baseline is you assume these 2 things are independent. Right? Once you assume they are independent, you can actually just multiply them together. Right? You have selectivity for the first predicate, you have the selectivity for the second predicate, you multiply them together. Right? That is your expectation of number of tuples you have, assuming these 2 predicates are actually independent. So that's something you could do. And you could do more, but let's take a break. And when we get back, we talk about more about cost models. Yeah. Okay, so let's continue. People on Zoom, can you give me a signal? Okay, perfect. Yeah. So as you can see, right, if you know which relation you want to estimate cardinality for, if you know a single attribute, right, so that's relatively easy, right? You can get a pretty good estimation, but just build a single histogram for that attribute. You can keep reusing it. It's fun. Why is the whole thing hard? The whole thing hard is because, first one, when you have these multiple attributes, right, you want to say, yeah, I want this multiple attribute to be like this. Tell me how many tuples you are going to have, right? So in this case, if you do not capture the correlation between these multiple attributes, oh, that's going to be very bad, potentially, right? Because you cannot always assume they are independent. And what's actually more important is when you have this query tree, right? So you are not dealing with the cardinality of a single relation, right? You only deal with that at essentially your leaf node. And then you have the things in the middle of the tree. You are talk about, yeah, how can we estimate the cardinality for a subquery. And then you have to deal with this correlation. So that is very hard. You cannot, you could, but it's going to be very expensive for you to try to capture every single pair of attributes, every single triple of attribute, every single quadruple of the attributes, right? And you can capture all the correlation. That's going to be very, very expensive. Okay? If you build a single, that's actually where the hardness and complexity of cardinality estimation comes from. That is, if you want to capture exponential many kind of configurations of the correlation of the relation, you need certain amount of space and complexity for that. Okay? So you can also do this for essentially continuous attributes, right? For example, you can say, you can build this continuous histogram, right? So you can put them into bins, right? You can say, so here's how many people with age 30 to 40. This is how many people with age 40 to 50. When you say, I have a query, try to understand how many people are between 35 and 45, right? You can make some assumption on distribution, right? Assuming they are uniformly distributed, so on and so forth, they can have your estimation. So if you really care about correlations, if you know which pairs of correlation are very important, you can actually build a multi-dimensional histogram, right, over just two different attributes. But the problem is you cannot do this for all the pair of attributes. If you do that, it's going to be way more expensive. But one thing people can do is they can actually, for example, compute the correlation between different attributes. They pick the best one, and then they compute their correlation, right? Have this multi-dimensional histogram, right? And then they say, all the other pairs, or all the other triples, for example, they are independent, for example. That's something people do in practice. So some of you guys are going to take the machine learning next year, right? So just remember this problem, cardinality estimation, because there are multiple problems inside database system could benefit from some machine learning models, right? You can replace many things by machine learning models. So and cardinality estimation probably is one of the most natural problems to be replaced by a machine learning model. Because what we are trying to do is to think about your data as a finite sample of some distribution, and you are trying to learn what that distribution really is. You are trying to capture as many pairs of correlation as possible such that you can recover that full distribution. So that is one of the actually pretty natural definition for many of the machine learning models, right? So if you take machine learning next year, remember this problem, right? So you should be able to make some progress on making that better. Okay, but assume that we know how to estimate cardinality. Once you have the cardinality, you know selectivity. Once you know selectivity, you can actually plug it into the thing we talked about on Wednesday, so you know how to estimate pretty much the cost of every single operator. Then you can actually put them together, okay? So it's very easy to say it. It's very hard to do it. If you look at PostgreSQL, there's actually a whole bunch of code just trying to deal with that. But intuitively, that makes sense, Now let's assume we know how to do that. That is, given a physical plan, we know how to estimate the cost. And then another question we want to understand is how can we do the search? Because given a single logical plan, there are so many different ways you can actually arrange the physical plan, give you something equivalent. Even though for each one of them, I know how to estimate the cost, it's still very hard for me to search through the space because there are exponential many possible plans that I need to deal with. So the search problem is also pretty hard for query optimization, simply because the search space is actually too big. And if you think, okay, so look at all the queries that we talk about in this course, how hard that can be, right? I have 3 different relations, I join them together, I try all the others. Yeah, it doesn't seem too big as a search space. But in practice, SQL query in real world doesn't look like the thing that we talk about in the course. The SQL query in real world often look like something like this. This is a query 14 of TBCDS, right? So this is a single SQL query. Okay? If you look at this, the amount of candidate physical plan, the different ways you can arrange all those joins, right, could give you a pretty big search space. Okay? So that is why searching the optimal physical plan could be pretty hard. So how hard that can be? Now let's consider this very simple example that I have an n-way join. I have n different relations. I want to join them together. And without worrying about like how to do joins, even try to come up with the optimal join order could be hard, right? How many joins order do I have, right? For these 4 different relations, I have these 5 different ways of actually arranging them, right? If you look at them, yeah, I can join the first 2 relations, then join with the third one, then join with the fourth one. But I can do the other thing. I can join the 2 in the middle, and then join with the first one, then join with the first one, so on and so forth. How many different ways you can arrange the tree, even if you only cares about the join order, which give you a very small subspace, right? Even that subspace have exponential many possible ways to arrange that. And not to say for every single operator there, you also need to decide what is the join algorithm. We talked about that last time, right? Then what you are going to have is actually for 4 to the n, that's many plan. For each one of them, you also need to decide, yeah, whether I should do next loop join here, whether I should do next loop join there, right? And this is without selection. This is without projection, only about join order. So the space that I need to search for is actually pretty big. So how can we do that? So once you deal with this really complex search space, you have to make some compromise, right? So the art of designing a system is to try to make compromise that doesn't matter too much. So there are multiple compromises people are doing. The first compromise people are doing is really try to constrain the search space. If you look at what people are doing back in the 70s, when people are building, for example, System R, the first relational database system from IBM, back in the 70s, what people do is to say, okay, I have some heuristics about the search plan that I like. You do not need to search for all the possible plans. Here's a subspace. So what they do is they only consider what they call left deep join tree. Instead of doing, for example, all the possible plans, they like the thing in the middle, that you only grow to the left. You first join the 2 relations, then join with the third one, join with the first one, so on and so forth. You just grow it. You do not do the thing on the left-hand side. You join 2, you join 2, you join the result of these 2. You do this left deep join tree. What are the rationales behind it? The rationale behind it is that if you consider this left deep join tree, it actually give you all the possible fully pipelined plans. That is, you do not need to save the intermediate result if you are doing an iterator model, right? Whenever you call the things on the next function in the root, you are going to call the next on the left-hand side, then you go down, go down, go down, then you propagate, right? Once you have this left deep trees, right, you can actually generate all the possible fully pipeline plans. And back in the 70s, that's very important, okay? And even today, that's also very important. So, and another thing is not all the left deep trees are fully pipelined, whenever you have this software join, like the software join in the middle, right? You need to save some result because you need to solve them, right? So not all the left deep trees can be fully pipelined, but can actually generate all fully pipelined plans. That's why people like it. And then what people say is, okay, forget about that really big search space. I only consider all the possible left deep trees. This brings the complexity down. It's still exponential, okay, but much, much smaller. So here, n is the number of relations that you want to join. So once you do this, right, the search process becomes this. That is, you enumerate all the possible join orders. You consider all the possible permutations of your relation, and then each permutation will give you a left deep tree, okay? Because you first do the first in the permutation, first two in the permutations, you join the third one, so on and so forth. You consider all the permutations, and then you enumerate the plan for each operator. You are doing a hash join, you are doing a salt merge join, so on and so forth. As you can see, it's still a very big plan. So, and then you enumerate access method for each operator, right? For example, whenever you are doing next loop join, you can do sequential scan, you can do B plus trace, so on and so forth. You also enumerate the access method. So this is actually, and then for each one of those plan, you use your cardinality estimator to estimate cardinality. You plug in the cost model, get the cost, then you get the best one. Okay? So this is the search process back in the 70s. So this can be done by dynamic programming. If you open a textbook, right, so there's that algorithm there. So essentially have an idea, you try to get a plan for one relation, and then you try to get a plan for two relations, so on and so forth. The whole thing is still going to be exponential, but at least this search space is much, much smaller compared with the one without any structure. Okay? Another compromise people might do is actually, instead of try to search all the possible plans, is by searching the space using heuristics. So this is actually something very interesting. People start to do that recently. If you go to Spark SQL, that's actually what they do. The query optimizer is actually very different from the cost-based optimizer we just saw. The high-level idea is actually giving a query. I do not really estimate too much of the cost. I have a sequence of rules that I'm going to apply to your query plan. And I don't care too much about the cost. Given a query, I always apply the same set of rules. Then I reach some other query plan, and then I just use that. It's a rule-based query optimizer. So, for example, the thing that we could do is given a query plan, we always do selection as early as possible. That is, I always push down selection as hard as I can, which makes sense, right? Why do I even need to search for that, right? I push down selection as a first step, and then I push down projection as early as possible, and then I perform the most restrictive selection and join operator before other operators. I have n different relations to join. Instead of searching for all the permutations that I could have, I will pick a pair to say, this is the most selective one. I'm expecting this join will actually give me smaller amount of tuples. Then I will do that first. And then I redo this process. I keep doing those joins of selection that return the smallest amount of tuples, right, as much as possible. The high-level intuition, if you look at the cost model we have on Wednesday, most of those operators, their cost depends on actually how many tuples you have in the input, which is a very natural thing to say, right? So, and then essentially, I keep doing those small things in the early stage, and then I hope the later stage it won't blow up. So that's the goal. And some systems only use heuristics. I think if you, at least 3 years ago, if you go to, if you go to Spark SQL, that's what they do. Given a query plan, just do the rules heuristic all the way. Then you are done. It's super fast query optimization method. And some of them will do a combination between heuristics and also a partial cost-based optimization, right? In real world, these two different ways to compromise this problem is actually can be combined. And also for the first compromise, if you really want to search a space, you don't have to do dynamic programming. You can do, for example, do those like evolution algorithm. You can actually have better search heuristics, so on and so forth. You have better search algorithm. And for the second one, we are doing this rule-based query optimization method. You can also do some query optimization for a sub-query tree, right? So in real world, it's often get combined. Okay. So when we talk about this, right? So this is just one example. So one really popular rule that people do when are talking about this, like one possible ways to apply all those rules is assuming I gave you a query, right, with a whole bunch of kind of selection predicate, theta 1 and theta 2 and theta n, so on and so forth over E. So what I do when I build a, I could do this, is I decompose this theta into a whole bunch of smaller select operators. I have selection over theta 1, selection over theta 2, so on and so forth. I have this. And then I push down as hard as I can, right? Now the predicate is smaller. I can potentially push down more, right? Because whenever I push down, I need to make sure that selection predicate only touch a single relation, right? The smaller the predicate is, the more I can push down, okay? I first decompose it into a smaller thing, and then I push down as hard as I can, and then I end up with a whole bunch of joins, and then I will try to take advantage of the fact that they are associative. Then I will search for those pairs that give me the smallest result. If you have projection, you also push that down as deep as possible. And then another thing is this can also give you essentially the structural plan. And then how can you pick the algorithm, the implementation to use for each of those operators in the tree? Yeah, you try to pick an algorithm that makes sure you can enable pipelining as much as possible. So this is just a very simple rule-based optimizer that surprisingly works pretty well in many cases. Okay? So these are the 4 things that we want to talk about when we try to build a query optimizer. Like again, we can use the whole semester to talk about query optimization. That's a very hard thing to do. But in principle, these are the 4 things. You want to understand what is execution model, how can you actually run a tree or DAG of physical operators, what is the cost model, how can you estimate the cost for each operator, and how to put them together. You want to understand the search space, what are the possible transformations I can do to transform an input plan into some equivalent plan that's going to give you the same thing. And then you try to have some search algorithm to really search the best physical plan given the cost model. So if you take a real-world database system, they often make different design decisions for each of this. But I would be really surprised if some of the system missing one of these dimensions. So these are the 4 fundamental aspects of query optimizer that we want to understand. Okay, now we can put all this together. Okay, now we talk about every single layer of database system. So what are we going to have here? The user, so we talk about this from a bottom-up way. Now let's start from the top. What do we have? The user gave me a SQL query. What I'm going to do is to parse it and then have a logical plan. A logical plan is a tree of operators, okay? It's not enough for the system to run it. The very first step of a system is actually try to do query optimization, produce a physical plan, which is a tree or DAG of physical operators. It's physical in the sense that for each of those operators, I also know how to run it. It's a sort merge join, something like that, okay? And then I have a physical plan. Once I have a physical plan, I need to run each of those operators. To run each of these operators, for each operator, I have a function called, for example, run or next. And then I'm going to call it step by step in the physical plan. Whenever I call it, I go to the second layer, the operator execution layer, tell me how to actually run each of those physical operators. And how does it implement that? Is by calling a whole bunch of things in the access method layer. You want to join, sequential scan this one, probe the B-tree index on this one. It's all those access methods. And for each of those access methods, it's going to fetch pages of the relation from the hard drive to the buffer. It's going to tell the buffer manager, say, I want that page in order to run this access method. And the buffer manager is going to check whether the page is the buffer or not. If it's in the buffer, it's going to return it. Otherwise, it's going to load it, evict some of the other pages and load it back and serve the access method layer. And whenever the buffer manager tries to load the page, it's actually talk to the disk manager, not directly talking to the hard drive. And then the disk manager gets a request, going to interact with all those files. We talked about structure in the last 2 weeks in the bottom-up way because that's easier to understand. Now, if you go from the top to the bottom, it's also pretty clear what database is actually trying to do. Make sense? It took us 2 weeks to go through every single layer. But yeah, I think we are getting there. In real-world database systems, you can actually investigate the query plan, which is a skill that's actually very important for all of us to have. So let's look at one very quick demo here. So assuming I have let's do this. I don't know how to hide this. Oh, it's here. OK, so this is a PostgreSQL instance. Oh, I got stuck. Yeah, need to redo it. We have time. Yeah, sorry, give me maybe 5 minutes to set it up. Yeah, so we'll go back home, right? So this is an exercise that you can actually do by yourself. It's pretty slow, but we will get there. I really want you guys to see the query plan. Oh, OK, so if any one of you guys are in the Cardinality thing, close it. Yeah. Let's do this. OK, so in PostgreSQL, so you can actually see the query plan. OK, so the way to do it is you have a SQL query that you want to run. Instead of running it, you have a special keyword called explain that you put that before the SQL query. Okay? So we have explain, then you follow by your SQL statement. And then what the system is going to do is going to say, yeah, this is the query plan I'm going to have for this SQL statement. In this case, just to make sure we're on the same page about what the query plan looks like, a query plan in PostgreSQL is actually going to look like this. Okay? So there are ways to actually kind of illustrate it in a more beautiful way. But essentially, the way to read it, because it's a tree, okay, you read from the leaf, which is the thing really toward the right-hand side, right? In this case, it's going to say, OK, so the first thing I'm going to run here is sequential scan. As you can see, this is actually the access pattern. Okay, as you can see, the sequential scan. I'm going to sequential scan on category C for some relation. Okay, so this is actually one access method. It's a leaf node. And then you go up. Then I'm going to build a hash table for that. Once I build a hash table, I'm going to do a hash join between this thing, this hash table, I'm going to sequential scan another relation. This is my hash join. Right? Remember hash join? You build a hash table for one relation, then you sequential scan the other relation. Right? So as you can see, once you do explain, this is actually tell you what the system actually going to do. And then you have this hash join, right? So, and then it's going to do another hash join because the three-way join with another relation, do the hash join, and then you sort it, you return the result, right? As you can see, for every single node, that is every single line in the query plan, you have the estimated cost, okay? This is actually how expensive the system is expecting that subtree going to be. And then you have this number of rows, which is the cardinality. Okay? How many rows I'm really expecting from that operator. And that is actually how all the parent node actually try to estimate the cost for you. And then you have the width, which is actually how many attributes that you are going to have. So this is a query plan in PostgreSQL. Okay? So whenever you have a SQL query, you can just write explain, then you are going to have something like this. Okay, so in general, right, so performance is a very complex issue in database. We talk about a very simple cost model for every single operator because we're going to have 2 weeks to talk about this. But in practice, it's actually more complex. Read and write, they are very different, okay? So they have different performance, different pattern, and depending on what type of hardware you have, they could be very, very different. So there's optimization of a whole bunch of things. You can cache the query result, right? You can have stored procedure, you have prepare statement, you can have something called materialized view, right? You can build indices. There's something called multi-query optimization in the sense that maybe there are multiple users running a whole bunch of queries. I can also optimize them all together. If all of the queries are trying to scan the same relation, I can batch that scan in one pass, for example. Right? There's multi-query optimization. There's a whole bunch of things. Performance for a database is a very complex thing. If you want to learn more, there's another course. I think I forget about this bachelor or master. It's called database system that we have, right? Which is going to go deep into every single layer. And whenever there's a new generation of hardware, you get a new generation of query optimizer, you get a new generation of operator execution, so on and so forth. So this is about query optimization. Okay? So in the last maybe 20 minutes, let's try to talk about another thing. And that is about tuning. Because whenever we are talking about data system in the last 2 weeks, we always assume there's a whole bunch of constants, right? Read and write are equally expensive, right? This is the I/O cost. This is the size of the buffer, so on and so forth. When we are writing a query optimization on a piece of query optimizer on a piece of paper, yeah, you can just assume it. They are a symbol. But inside the database system, right, that's something that you can actually configure, right? And depending on the value you gave to the system, you are going to have very different performance speed of running a query. And the way of getting those optimal configuration is called tuning. So it's just actually try to close this loop. Once the user knows how the database works, the user can actually talk to the database to really set up the optimal configuration. So this is a very hard thing to do, okay? In PostgreSQL, right, there are actually almost 180 different things you can tune, okay? So if you're really curious about tuning, there's a 3-hour video about how to tune many of those. But here we are talking about a little bit about intuition, about things to do. Now let's think about this query, okay? So we don't have this live demo, but let's think about this query. It's a very easy one. I have 3 different relations, okay? I have artist, I have releases, and I have release by. These 3 different relations. I want to do a natural join between them and return all the result. Without knowing too much about this, if you issue this query to the database, what do you think the database will do? Assuming we are doing something kind of in the average case. We don't know the join order. Let's not deal with the join order. What join algorithm do you think database will do for you? on normal computer. So that's something you could try when you go back home. But if I must guess, in this case, because all the predicates are actually equality, you are checking whether they are equal or not. This is a natural join. On most of the machines, if your database, if your relation is kind of normal, in the sense that the distribution is not too skewed, something like that, probably it will try to do a hash join for you. Okay? So that's something that we talked about in the last lecture. Hash join could be very, very efficient. We did an exercise about counting the number of IOs compared with sort merge join, right? Slightly better, right? Everything being equal, highly likely the database will do hash join for you. What if you don't like that? What if you know that you can do better, right? Sometimes database do that automatically, but you are human. Sometimes you know better. One thing you could do is inside database, there's a one configuration you can set. It's called work memory. The way to do it is actually tell the database, okay, so this is, oh, sorry, I was being, sorry. I really need a live demo. Okay, okay, sorry, yeah. So there's one thing called work memory. So that's actually how much memory the database system can use, okay? And then you can tell the system, okay, this is how much you can use. You can make that bigger. You can make that smaller, okay? So let's try to reason about how does this value going to change our query plan. Assuming I have this one that's really big, reasonably big, like 4 gigabytes is probably too big, like 400 megabytes, something like that, right? Then highly likely, probably, the system going to do hash join for you because your hash table going to fit into that work memory. What if I make that really small? I make that, for example, 10 megabytes. How are we expecting the query plan to evolve? In this case, you can actually try that by yourself when you go back home. When you make that smaller, you can actually see at some point, if you explain this query, you are actually going to favor more and more doing sort merge join, because that thing requires a fewer amount of memory. Okay? When the work memory is big enough, can hold a single hash table, you can actually see how the system start to prefer more and more hash join. Okay? So that's something you can actually try when you go back home. It's very unfortunate I cannot show you that evolution. That's just a tipping point that smaller than that is going to be sort merge join, bigger than that is going to be hash join. But trust me, okay, I'm not trying to trick you. Okay? When you go back home, try that by yourself. And you can actually do more. So you can actually tell the system sometimes that I do not want you to do hash join for whatever reason. I'm a user, right? You are a system, right? I tell you, you cannot do hash join. Right, so there's a one configuration you can actually set. For example, enable hash join, you can just set that to 0. So once you have this, the query optimizer will know, okay, I will not do hash join. You can also set merge join, sort merge join to 0, right? And you can set the cost of those like random page access. Okay? You can set that to be very, very expensive. So let's try to reason about this case. Assuming I tell these 3 things to my database, what would be the plan? How do you think David is going to do, right? So in this case, alpha case, the random access is super expensive, okay? And usually that number is like 4 or something like that, okay? So I change that to a very big number. I disable hash join, I disable sort merge join. If you run explain, what would you have? So if you try it, highly likely the system is going to say, okay, I'm going to do nice loop join without using any index. It's going to have a whole bunch of sequential scan of your relations. Why? Because first I don't have a choice. I cannot do hash join, cannot do sort merge join. The only choice I have is probably nice loop join and also nice loop join using index, like using, for example, like a B-tree index. Right? Because your random page access is so expensive, my random probing of the B plus tree is very expensive. So in this case, I'd rather do sequential scan for my next loop join. Okay? When you go back home, if you do this, probably highly likely, yeah. So I'm almost sure it's going to give you kind of like sequential scan next loop join because I just tried that 2 hours ago. Yeah. So what if you make the random page cost smaller? You say you cannot do hash join, you cannot do salt merge join. My random page cost is 0.1. I don't know whether you can give floating point. Like for example, it's 1, for example. Then what would you have? In this case, you will also see the query plan start to change. It starts to favor next loop join because it doesn't really have a choice on algorithm, but it starts to use your B plus tree in this case. Because then when your random page cost becomes smaller, okay? So the random probing and random tuple fetching from the B plus tree is not that expensive anymore. So essentially what you can do inside your database system is try to give the database system a whole bunch of assumptions that you have. Sometimes database system try to do that for you by default, okay? But sometimes it's a system, sometimes it makes a mistake. And you, as a human, knows more things than a database system. Sometimes the Cardinality estimator make a mistake, try to pick a different query plan. And you say, yeah, that doesn't make sense, right? So you can actually try to send in all those signals and try to make the database reach a better query plan that run your query faster, okay? So that's something you can do when you go back home. Sorry, the demo doesn't run. But trust me, yeah, what I say is highly likely is true. I just tried 2 hours ago. Okay, great. So that's all we have for today. That's actually all we have for the database system. Okay, now you know how to do, now you know what happens when you issue a SQL query. Starting next week, we are going to talk about a very interesting concept called transactions. Okay, so that's all for today. I'll see you guys on Wednesday.